And it is now my pleasure to introduce our closing speaker. And so let me introduce him and say a couple of words. So our closing speaker is Dr. David Estrada. He received his doctorate in electrical engineering from the University of Illinois at Urbana-Champaign, where he was an NSF Graduate Fellowship Research Fellow, a National Defense Science and Engineering Graduate Research Fellow, and a Micron Graduate Research Fellow. David always loves to have many things associated with his name at any one time. I will say before that, he was a Boise State undergrad. And so he has come back to Boise State. After completing graduate school, he joined the faculty at his alma mater here in Material Science and Engineering, where he's currently an associate professor, and he holds a joint appointment with the Idaho National Laboratory and serves as Boise State University's associate director for CASE, the Center for Advanced Energy Studies. And so I know some of our undergraduates who are in an RAU working with CASE. That is partially thanks to Dave for writing that grant proposal and getting funding for that. And as I said, he likes to have multiple titles after his name because David always is doing lots of things. He's published a bit. That's a bit of an understatement. You could tell we got this from Dave. And some papers being better than others. I love it. And some work leading to US patents. Again, humble. However, he believes that the best part of his job is working with students in research and providing them opportunities for discovery and professional development. And that's probably one of the reasons why there was excitement about inviting Dave to give this closing talk, because I know how much David supports students in their research. So Dave, it's all yours.
Thanks, Donna. Can you hear me okay?
Yep. Great.
Yeah, big shout out to the KSRU students. Excited for you guys to be closing out your experience, and to everyone here. Just acknowledge the CASE folks because of my connection there, and then the McNair scholars. I have a spot in my heart for the McNair program, as you'll hear about in my remarks as well. But thanks to Dr. Llewellyn and her team for inviting me to speak with you today. I don't necessarily like having a lot of things associated with my name, but it just happens that way. So it does take a lot of time. So unfortunately, I didn't get a slide deck to share with you, but I just have some remarks, and I do have a couple slides I could share maybe towards the end if we need to. But I think undergraduate research was a transformative experience in the development of my own STEM identity, and I'm honored to have witnessed the evolution and growth of undergraduate research in Idaho, particularly at Boise State University and under Donna's leadership and her institute. It's just been tremendous growth, and the ICUR event when I was an undergraduate at Boise State did not exist, right? So to see the whole state come together and celebrate your summer research experience is really great. It shows a lot of growth for Idaho. So I'm just going to give you a little bit of background, my own personal story. I'll touch on my own involvement with undergraduate research, and then I'll talk to you a little bit about what I'm doing now. And I don't know if the Materials for Society folks are on, but we have a couple of the Materials REU students also working in my lab and in some of the healthcare areas. But I am the youngest of 6 children, born of Mexican immigrants. My father grew up in poverty in a single mother household with 8 siblings. And at the age of about 7 years old, he had to quit going to school so he could support his family. The task was really difficult for a 7-year-old, right? And he ended up losing 2 of his brothers to starvation. My mom, she was slightly better off, but she also had to quit school before completing a high school education. At that time, you had to pay for your chemistry lab fees, and her family couldn't afford it, so she had to drop out of school. So these experiences, in part, motivated my parents to seek greater opportunity for their children by immigrating to the United States around the mid-1970s. As time passed, my parents became U.S. citizens, and my siblings began to graduate from high school and move out of the house to build their own careers and families. I was the last to graduate from high school, marking a major accomplishment for my parents. They had succeeded in seeing all of their children complete the high school education that they had hoped for. Following high school, I spent 6 years in the United States Navy, with the majority of my time spent overseas. There's lots of experiences in the Navy. I got to travel around the world quite a bit. Most of my time was spent in Japan. I was forward deployed to 7th Fleet out of Yokosuka, Japan. And so several of those experiences, they stand out, but none has had such a lasting impact on my personal growth and my career choices as a visit to the tiny island of East Timor. I think many of you might be too young to remember the civil war that happened in Timor back in 1995. But the USS Curtis Wilbur, to which I was attached, was tasked with rebuilding the elementary schools after that war. And when we landed on shore, I was shocked at the conditions and the challenges that Timorese children endured in order to receive an education. The city sewage system was basically just a bunch of ditches, a network of open ditches, which ran alongside the city streets and open air markets. So basically, you have your butcher shop right next to all the crap in the ditch, right? So it's a breeding ground for diseases such as cholera, dysentery, hepatitis. They just gone through war, so there's still bullet holes scattered across the outer schoolhouse walls, just serving as a reminder of the political violence that surrounded these children's lives just a few months before we arrived with the United Nations. Despite their neglected educational environment, the children still managed to come to school, eager to learn and hopeful that education might help change their situation. And so during my visit, I saw despair, but I also saw hope. And it was the first time in my life that I really understood that for many people around the globe, the pursuit of education involves great personal risk. But it's a risk that they're willing to take if they're afforded an opportunity to pursue their education. This was near the end of my time in the Navy, and this experience changed my life, and it really factored into my decision to separate from the US Navy. I was no longer content with just serving my country. I really wanted to serve humanity and have a broader impact by using my technical skills to help solve problems which have no regard for political, socioeconomic, or cultural boundaries. So I received an honorable discharge in 2004, and that's when I returned back to Idaho to pursue a degree in electrical engineering at Boise State University. During my time at Boise State University, I was able to participate in the McNair Scholars Program. This program is basically a graduate school preparatory program, which helps students of underrepresented populations and underserved populations prepare to pursue graduate studies. Not only did the McNair program teach me about the possibilities that come with a graduate degree, they helped me get involved in undergraduate research. Through McNair, I learned about the summer REU programs, and I was able to participate in a NSF REU program at the University of California at Berkeley, where I helped design the control systems for a 3-phase Stirling engine for solar thermal electric energy conversion. I got really excited about that research, and I returned back to Boise State University, where I wanted to continue doing undergraduate research. I was able to join Professor Bill Knowlton's lab, who served as my McNair advisor, faculty advisor, and we investigated gate oxide reliability in 90 nanometer silicon CMOS. This is a really old technology, so I'm really dating myself now. But at the time, it was pretty state of the art for the semiconductor industry. And this was the topic of my first journal publication, which came out in my first year in grad school. So in 2007, I became the first in my family to earn a college degree. And I pursued my PhD at the University of Illinois, Urbana-Champaign, and graduated in 2013, also with all electrical engineering degrees. But my focus was on semiconductor device physics, which is a pretty interdisciplinary field. And that allowed me to join Boise State as a faculty member of material science and engineering. I leveraged all that knowledge and my expertise in nanomaterials to build a program now where I work at the intersection of emerging nanomaterials and healthcare, energy, and water. So my lab at Boise State is called the Advanced Nanomaterials and Manufacturing Lab. We're also bridging out to Eastern Idaho with the Center for Advanced Energy Studies, where we built some additional labs to further our research in collaboration with Idaho National Lab. Our lab is devoted to developing material manufacturing solutions for emerging engineering problems which have no regard for political, socioeconomic, or cultural boundaries. We believe research with such important humanitarian implications begins with an appreciation for the many different people and cultures around the world, and a deep understanding of the potential impacts of nanotechnology research on society and the environment. From the place of awareness and appreciation, develop the possibilities for the most beneficial global partnerships and collaborations. Like I said, we work on these grand engineering challenges in healthcare, energy, and water, with an eye towards developing manufacturing solutions so that we can translate research into the Idaho economy and the national economy, and hopefully make a little bit of money on the royalties from the patents. We are a pretty diverse team of researchers from across the world, including students born and raised in Idaho, some from Africa, Pakistan, Iran, all around the globe. So some of the work we do in healthcare, we are using nanomaterials that are 1 to 3 atoms thick to develop inks for printing smart bioscaffolds that can communicate with stem cells through electrical, mechanical, or thermal signals. Our goal is to be able to print patient-specific tissues, reducing the need for organ donors that treat end-of-life conditions reliant on organ transplantation, as well as musculoskeletal disorders such as osteoarthritis. In the energy sector, we're working with the Idaho National Laboratory and NASA to develop nanomaterial inks to print sensors that can peek inside nuclear reactors or be used to manufacture electronics on the Idaho or the International Space Station. Recently, we deployed some of our printed sensors in the nation's TREAT reactor, where we were able to measure directional neutron flux for the first time in the 60-year history of that national asset. So it kind of shows how using advanced manufacturing techniques can still help enable fundamental discoveries in some really old instruments. Relative to ISS, the International Space Station intends to deploy a materials printer to print electronics in 2025. Our inks have been outside of the ISS in preparation to deliver functional materials for those printing demonstrations in a couple of years. Alongside all this, we really need to learn how materials behave under extreme pressure, temperature, and radiation environments so that we can develop these materials and 3D printing approaches for the next generation of nuclear reactors that are capable of producing large amounts of clean energy and not relying on intermittent environmental factors such as wind and solar to enable grid scale energy storage or energy solutions. We also want to enable in-space manufacturing of the electronic systems and sensors so that astronauts can easily repair equipment failures on station. They can design custom sensors for space exploration or print biosensors for monitoring human health while in space. Water has been a fairly new area for us. I think it's going to be one of the biggest challenges for society moving forward. You can just look at some of the media surrounding South Africa, for example. Just a couple of years ago, they had day zero where the reservoirs that supplied Cape Town and or parts of South Africa went dry, right? So you can see the long lines of folks waiting to get fresh water. We've actually worked with the Idaho National Lab and Drexel University to show that a new class of materials known as MAXenes, these are transition metal carbides and nitrides that are just a few atoms thick, that they can remove ammonia from simulated wastewater streams. So think of that center part of the periodic table and then carbon and nitrogen, and just being able to create materials that are just one or a few atoms, 3 to 5 atoms thick. Our technology, our patented technology, was 10 times more energy efficient than state of the art, 100 times more absorption capacity for target ions. And we only use one of these materials. There are thousands of these that are predicted. 50 of them have been experimentally realized. And so it's just a playground right now in trying to see what these materials can do to solve such grand challenges. We've already had interest from companies in California, Switzerland, and Sweden to license a patent and further develop our technology for industrial scale recovery of ammonia. And the State Department recently highlighted our technology during an economic partnership visit to Southeast Asia. So while these topics are important and have potential for broad impact and fundamental discovery, I'd say the thing that has excited me the most about my 10 years as a faculty member at Boise State has been the opportunity to work with students and engage them in the research process. I've been fortunate enough to mentor undergraduate students and high school students from all sorts of backgrounds. Some of these students have interned with my collaborators at NASA, Air Force, or Fortune 500 companies. Some have earned highly prestigious fellowships and gone on to pursue PhDs from Stanford, Berkeley, or Princeton. One of my former undergraduate students even served on a presidential subcommittee to advise the president on issues in advanced manufacturing. These are their accomplishments, not mine. I'm just happy that we were able to provide them an opportunity to pursue their dreams and their research that led to this type of success. The one thing that all these students had in common that enabled them to do this was a passion for discovery, a hard work ethic, and a desire to use science to help solve societal challenges that are going to have a broad impact on humanity. I hope that your experience with your summer research programs, with the Idaho Conference on Undergraduate Research, that it ignited a passion in you so that you continue in research. We need your help to solve these tough problems, which have no regard for political, socioeconomic, or cultural boundaries. It's going to take a wide range of disciplines to solve these grand challenges. It's not just a single solution from a single discipline. So go back to your institutions, stay involved in research. Whether you complete a bachelor's and go to industry or academia, continue on for a PhD in academia, keep in mind that work on problems that are worth it, right? We need your expertise, we need your knowledge, we need your talent. And when I say we, I mean humanity and society, right? So thank you for your time. I know I only had about 10-15 minutes, so hopefully I'm within those constraints. Well, thanks, Donna.
Thank you, Dave. Super. Thank you so much. Such inspiring words for the close of our conference.